So FYI, I forgot to record this. I've just shown that the magnetic force on a closed loop is 0 if the field is uniform. You can almost tell from the notes that this is indeed the case. Okay, I want to continue with the discussion we just got started with. I couldn't get to the meat of the problem. It was an example problem, and let me write down the example number. It's 5.3. So in this problem, you have a region of magnetic field that is into the board, and a loop is suspended, and you want a current in the loop. So this has a mass m. Maybe this is just a battery that sustains the current in the loop. And you do ideal cross B. On this end, you have I this way, B into the board. The force is to the left. Oh, I shouldn't say, just on the top portion where there's a magnetic field. So these are all magnetic forces. But on this side, there's an equal and opposite force. So if this is a rigid loop, then it's not going to move sideways. On the other hand, over here, I would get an ideal cross B. And I would get a force here. And this is the one that's important. If you tune the current precisely, you can get this object, this loop, to just float. And what is the magnetic force? So this is F, let me write this as magnetic, because of course we have weight. So just the magnitude. It's IdL cross B. Everything here is uniform. This loop in the problem itself has a length of A units. So it is I, which is constant in the loop. Integral of dl is simply the length A times B. And indeed, if IAB equals mg, we get that the loop floats. We had also discussed that the net magnetic force, sorry, not magnetic force, the work done by the magnetic field is 0. Question mark?
This is a distinction that I don't think I caught the first time. The magnetic field is only above that box.
Correct.
That's what qualifies it.
Yep. Let me make that very clear. We don't particularly need that diagram now. So that's the region where the magnetic field exists. That is simply to avoid unnecessary complication. And we have also seen that the work done by the magnetic field, the magnetic force, is 0. So now what we're going to do is slightly dial up the current. And all of a sudden, IAB is not equal to mg, but rather it is more. So the magnetic force is greater than the weight, and the loop simply goes up. The question is, who does the work? And as I mentioned before, there's one part of the answer that should be clear. We know who does not do the work. It's the magnetic field. So let's try to make sense of actually what's going on. But the work done itself is simple enough to understand. It is simply mgh. So assuming that the loop has moved up h units. Okay? And we won't wait till the loop, the lower part of the loop enters the magnetic field. We don't want unnecessary complication there because we might get a downward force. But that's not the point we're trying to make here. We're trying to see, as the loop is going up, there is a work done. So how do we reconcile these two facts? The answer is very simple. To dial up the, when you dial up the current, or I don't mean dial up the current. The current is larger, but the battery has to work harder to sustain the current. Okay, so this, consider any point in the loop at a given time. So this might translate to, let's say, this point. And just let's look at what's going on. First of all, there's a current through the loop. So what you have here is I, which is lambda times, I'm going to use W for velocity. So lambda times W. There's a current in the loop. We know that already. But the loop is moving up. So this point also has a upward velocity. Let's call that U. Although the net speed, the net velocity, the expression itself is not important to us, we will have a net velocity for, which is nothing but the vector sum V plus U. The horizontal plus the vertical. Okay? Now, the magnetic force is always perpendicular to the net velocity. So the magnetic force, which way is the magnetic force? Place the edge of your right palm along V and curl your fingers towards B. Just going to make this exaggerated. And that magnetic force has two components. That magnetic force has this, the horizontal component, remove the clutter, and a vertical component. The vertical component itself will lift the loop. Again, you're going, wait a minute, isn't that the magnetic field? Well, hold on. But these charges are now being pushed back. Yeah? So that means to keep a steady current, the battery has to apply an equal but opposite force. Yeah? And this is always the trick about calculating. So let me, lack of a better term, let me call this, at least the magnitude, it'll be the opposite. I want to say F battery, but I'm writing only the magnitude. The force is this way, the battery is pushing it that way. Okay, I don't want too many, we'll have to keep the vector direction in mind intuitively, not overburden our notation. What is the magnitude of this force? So maybe I can even put this way. So the battery has to maintain the current, the battery has to do an equal and opposite force. Yeah. So this is also good practice for magnetic fields. Magnetic force is perpendicular to the velocity and the magnetic field. The magnetic field is fixed. So this velocity creates that force. And this velocity creates this force. Because, let's do it, this one. On the other hand, this one. So this force is created by the lift. How much is the lift? Well, it's ILB. It's not quite I, but the vertical I. So let me do the L and B. The current itself in the wire is LW, but this vertical current, if you will, there's no loop there, but because the whole thing is moving up, it is LU. Yeah? Now, so this is extra force applied by battery. That's the subscript B. So let's do the work done by battery. This is always F dot dr. We don't have to again keep track of vectors. Everything is in one direction. So it's going to be L U A B. Let me temporarily call it dx, if you will. But then I can write that as lambda A lambda U A B dx dt times dt. This problem was almost done, so I can erase this part. The integral itself is easy. I'm going to bring lambda out, u out, a out, b out, and dx is nothing but the horizontal velocity. Dx dt, sorry. This dx dt. That is just w dt. Yeah? I'm going to, well, I shouldn't have brought the u out, but you live and learn. So I'm going to bring the w out and u in. They're all constants. So w out, a, b, u, dt. This is the current. AB, this is the vertical displacement. Well, that's just height. Yeah? We had previously shown that this is, what is that? IAB. So the work, just the raw expression kind of works out. Well, that's fine. It seems like we have manipulated all the numbers we want, just so that we get these things to balance out. How does that work? Here too, Griffiths does a fantastic job of a simple explanation that we know from mechanics. Suppose you have an inclined plane, a smooth inclined plane. There's no friction. We don't need to worry about friction. Yeah? Smooth plane. And if I push on this box, what's going to happen? It's going to start moving because it's smooth. Which way am I pushing? Horizontally. Which way is the block moving? It has a vertical component. Who is doing that work? Still me. The normal force simply redirects this one so that the block is able to move upwards. You can set up your coordinate system and do this calculation if you want. Clearly, this has a vertical component and a horizontal component, so the block is going to move upward. Now that is possible only because of the normal force. So here too, the battery does the work. The magnetic field simply redirects the force. Yeah? And that is why, of course, more complicated in math, that's why you can take a magnet next to another magnet and get it to move. Otherwise, the puzzle would constantly remain, who is doing the work? Well, you are, not the magnet. The magnet, of course, is simply redirecting all of this. So I haven't seen a better explanation of how these things actually work. Remember, most of the times to actually carry out the detailed computation, it's very difficult. Okay. We've talked about current in a wire. I think I jumped into it hastily, only because I'm assuming that you know current from freshman physics. Current in a wire. But you can actually have surface currents and volume currents. And surface current, I think I can draw reasonably well. Volume current maybe with a little effort. So imagine you just have a sheet, a conducting sheet or something like that. And current, I don't care which direction, but let's say the current is moving from here to here. So I'm going to focus on a small strip of the current that might be relevant to us. So yeah. And there's in this strip, the current vector is something like this. I can even put, since, well, what we'll do, since this is a small strip, instead of I will call it delta I, because the current is on the entire surface of this. Okay, so let me even call it delta I for the moment. just the amount of current in the small strip. And let me make it a vector too, because you know which way the current is flowing. And if you go to a different location, the current may be flowing in a different direction over there. But we're just focusing on this particular strip. Okay? This part that we have considered is to be perpendicular to the current. So let's call this delta L, and I'm going to put perpendicular. The vector K is defined to be, when in the limit delta goes to 0, so it is defined to be not L, I. So that's why it's a vector. The current flowing per unit length. Let's see what that is. Let's just do this in magnitude. We know how to put vectors. And what I'm going to do to make the discussion easier, I'm going to call it delta I over delta L perp. So to do delta I, what I need to do is get the charge in that crosses this in time delta t, and then divide by delta t. So I have to do a delta t first. There's this already. All I need now is the charge crossing that area. And let's assume that the speed here, the velocity is v. In time delta t, whatever charge could have moved in distance delta t would have crossed that barrier, correct? And it is the surface charge density times this area, some delta x times delta L perp. The L perps cancel, and in magnitude we get sigma delta x over delta t is v. We have intuitively done everything in magnitude, just keeping track of that one dimension. So vectorially speaking, this is the surface current density. Yeah? Okay. So recall, on a single charge, that's the magnetic force. So what would be the force on a current sheet? Obviously, I have to add up all the strips. Q becomes sigma dA. V cross B, or we get the analog, let me do it one more step, cross B, D, and this is K cross B yeah? This doesn't enter what we do on a regular basis, but the volume currents are important to us. So let me just discuss that. You can have not just current, you can just have currents in space, just filling up a volume, right? So volume, current, density. In this case, instead of K, we're going to use J. Volume, current, density vector. This is defined to be I divided by, look at this, it's one dimension lower, right? This is area current, so you divide by the perpendicular length. So over here, what is the perpendicular feature? It's a surface. So you divide it by dA perp. When you do that, you will get the exact same analogy. Don't even make it too complicated. You would get J, not, we had lambda V, then we had sigma V. Can you guess what this is going to be?
Rho V.
Rho V. This is in fact the original Rho V, right? As demanded by nature. And the force, again, magnetic force, is going to be what? Remembering again, Griffith's volume element is d tau. The only thing I always forget about Griffith's notation. So let me do one small result, and then we'll do some problems. And I think I'll wait for next class to do problems. But a very important result. I also realized that I haven't given you homework problems for the semester. This is a very important result. The continuity equation. Suppose I have an area. And I have this J vector here. Just from here, the current, I'm only doing the magnitude, is going to be, I'm just integrating this guy and multiply these two. Well, this may be a meaningless concept for the moment, but I'll sort of fix it. D I don't care about the magnitude. I actually want to know what's the current flowing out of the surface. So I'll just do it this way. Well, so what I'll do is see, the perp just goes away because what is the A perp? It is already the perpendicular component, right? From divergence theorem. So the dA vector is simply you take the dA and then take the perpendicular direction. And then you're taking the dot product. So that is the current flowing out of a surface. And then, I really recall only a couple of nice results in E&M. Divergence theorem, Stokes theorem. So what I'm going to do next is I look at this and go, that looks like divergence theorem to me, but you have to use a closed surface. Well, let's pick a closed surface. And then let's do J dot dA. Well, why do I want to do that? Well, I just told you I want to use the divergence theorem. I don't know what this means, but all I know is this is divergence of J d tau. On the other hand, I know current is nothing but the rate of flow of the charge density. Almost. Let me explain. So I'm leaving a little space for a reason, as you can tell. d dt. Remember, current is dq dt, so total charge. But if current is flowing out, what is happening to this? The charge is decreasing. Current is flowing in, the charge is increasing. But if I do it this way, if rho is decreasing, I don't get a negative. If rho is decreasing, if rho is negative, or rather if this is negative, I don't get a negative, it's not a negative current. Current is flowing out. So I have to insert this. This will ensure that whatever flows out is compensated by a change in charge inside that volume. And why should that balance occur? Because you cannot create charges in a volume. If it's flowing out, the charges have to decrease. Well, so then I combine these two, get a beautiful result. It's in every field theory of physics, there's this type of an equation. And I'll show you some of its elegance as well. So, well, that's easy. I'm going to do this. And so I get divergence of J d tau is equal to negative. I'm going to take the time derivative inside. So I'm going to do du rho. It becomes a partial derivative, right? Because rho is a function of x, y, z, and t. That's one way to write this. Or I can write it as divergence of J plus d rho dt d tau equal to 0. This is true for every volume. What does that mean? That means the integrand must be 0. Now let me write it in a way I like it. There are two kinds of relativists. Relativists who put time before space, other relativists who put space before time. This has a quality that we haven't seen very often before. For one time-like derivative, you have one space-like derivative. This is the heart of relativity, where space and time are considered to be equals. They enter into equations. This is called the continuity equation. It really is nothing more than, as you have seen, conservation of charge.